All right, what we're going to talk about now is the final topic that you will need for the last test, and that is shift registers. Now, for shift registers, we're going to start with our old friend, the D flip-flop. So the D flip-flop, as we remember, is very straightforward. When you clock it, so this is positive edge triggered, so whenever a positive going transition appears at the clock input, the flip-flop will take what's on the D and just put it on the Q. So if I put a 0 on the D and I clock it, the 0 will show up here. If I put a 1 on the D and I clock it, then the 1 will show up here. So what we're going to do with shift registers is we're going to take several D flip-flops and we're just going to hook them together like this. So if I have 4 D flip-flops, this will be a 4 flip-flop or 4-bit shift register. These are all the same. Now, to make a shift register, I'm going to connect them like this, which means every Q will feed the D input of the next one. So even though I've created this 4-bit shift register, the D flip-flops themselves behave like D flip-flops always behave. So I'm going to hook all the clocks together because we want to create something that is synchronous. And again, when we talk about synchronous in this context, we just mean that all the flip-flops are getting the same clock signal. So the same clock is going to all 4 flip-flops. Now, if I put something on here and I clock it, that will appear here. And if I clock it again, this one will come over here. And if I clock it again, this one will come over here. And if I clock it again, this one will come over here. So you can store a 4-bit value in here, but because we only have one input, so this would be, we're going to look at 4 different configurations, but this would be serial in, serial out. So that's the first configuration we're going to look at. And what serial in, serial out means is that there's only one data line or one input. So I can load into this 4-bit shift register. You can almost, I suppose, think of it as a circuit that has 4 bits of memory. So if I have a value like 1001, let's say, and I want to load it into this shift register, I only have one data line, which means I have to put a 1 here, and I clock it. This 1 will come over here. Then I put a 0 here, and I clock it again, and this 1 appears here. This 0 will appear here, 0. And then I put another 0, and I clock it again, and this 1 comes over here. This 0 comes over here. This 0 comes over here. And then finally, I'm going to put the 1, and if I clock it again, this 1 that was here now goes here. Then this 0 comes over to here, this 0 comes over to here, and this 1 comes over to here. And now that 1001 has been loaded in my shift register. So the advantage of serial in, serial out is I only need one data line. The disadvantage of serial in, serial out is that I need 4 clock cycles to load that value in there. And if I want to get it out, I need 4 more clock cycles to get it out. So in terms of what the D flip-flops are doing, they're doing the same thing that a D flip-flop always does, which is whenever they get a positive going transition at their input, they take whatever's here on the D and pop it over onto the Q. That doesn't change. Now the second configuration we're going to look at is a faster way to get the data out of it. So again, if I want to load the value 1001 in there, I have to put the 1, clock it, 0, clock it, 0, clock it, 1, and clock it. Because this is basically our input, and this is basically our output. So because we only have one line of input and output, I need many clock cycles to get the data in, and I need many more clock cycles to get the data out. So what you gain in simplicity, you lose in time. So the other thing we could do is serial in, parallel out. So it still takes me 4 clock cycles to get the data in, but if I want to get it faster, I could just put an output on each one of the queues. And then after I've spent 4 clock cycles putting 1001 in there, if I can look at all the queue outputs, I would see the 1001 immediately. So it takes me 4 clock cycles to get it in, but once it's in, I can see all of the data. Now, the disadvantage of that, of course, is you need more data lines. So instead of just having 1 output, now you need 4 output lines. So that's serial in, serial out. And if you put an output on each one of the queues, it's serial in and parallel out. So you can also kind of look at this as a serial to parallel converter, right? Because I put data in serially and I get it out in parallel. So in essence, you're converting serial input to parallel output. So you're converting serial to parallel. Now, if I want to put the data in faster, I need 4 data lines. The problem is I can't do this, right? You think, well, why don't I just put an input on each one of the D inputs, right? So I've got input, 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 input. Then I could load 1001 on my inputs, and then that would be parallel in. But unfortunately, you can't do that. And the reason you can't do that is because you're tying an input directly to an output, right? So if there's a 1 on here, and I try to put a 0 on here, you would have what they call contention, right? I can't have a 0 and a 1 in the same place at the same time, so they have to be isolated. So if you want to do parallel input, you can't do it this way. So what you have to do is you have to have a separate circuit and condition for the input and one for shifting. So what that means is you can't have the Q going directly to the D because, again, you're going to have that contention. So you kind of have to electrically isolate it, and we're going to use our decoder to do that. So I'm basically right now just going to zoom in on what we would have to do here if we want this to work. So if you have, so this will be the first flip-flop. I'm just going to give myself more space here to kind of zoom in on what's going on. So we know that when we want this to shift, the Q has to go directly to the D. But when we want to load something, we have to have an input that goes to the D, and we can't have the Q and the input both going to the D together at the same time, because again, you'll get 1s and 0s bumping into each other, and you'll have what they call contention or bus contention. And you know from working in the lab, if you try to put 5 volts and ground together at the same time, that never ends well. So how do we do this? So what you need to do is to have a mechanism where you can load when you want to load and you shift when you want to shift. So we're going to use a decoder, just a 1 to 2 decoder. So what we're going to do is we're going to have an OR gate going to the D input. And we're going to have two AND gates, the outputs of which will go to the input of the OR gate. And what we're going to do is we're going to take the input and make it the input of this AND gate, and we're going to take the Q and make it the input of this AND gate, and then we're going to have a small decoder circuit. So we're going to go directly to what do I want to do? Load is 0. So we're going to put an inverter here, and this straight in, and then this will go to an input called shift load, and we'll put a bar over the load. So this basically gives us the isolation that we need when we want to load data or when we want to shift. So we talked a little bit about this decoder circuit when we were talking in counters, when we were talking about counters. So if the shift load is low, right? So if I put a 0 here, then that means that I'm going to have a 0 on this AND gate, and I'm going to have a 1 on this AND gate. That means that this AND gate basically will be disabled, because we remember from our theorems that if we have 0 and A, that's 0. So because there's a 0 on this AND gate, we know this is going to be 0. So basically it doesn't matter what's coming in here. If you have a 0 on an AND gate, the output will be 0. And again, we remember that from our single variable theorems. However, this AND gate, because there's a 1, when you have 1 and A, the answer is A. So that means that if I have a value here that's A, because this is my load, so this is what I want to load. So if I have A and 1, the answer is A, so that means this will be A. And then if I look at my OR gate, if I have A or 0, the answer is A. So that means that whatever I put on this load input, that is what's going to make its way to the D. And this Q input, the Q output here going to the D will be disabled. Okay? So that's how you load. If you want to shift, so once you're done loading, get rid of these. Once you're done loading and you want to shift, then you put a 1 or a high on the shift load. That makes this 1, that makes this 0, so this gate is disabled. That makes this 1, so this gate is enabled. So now I have Q here, and if I have Q and 1, then the answer is Q, which means this Q is coming out here. This is going to be 0 because I have a 0 on this AND gate, so this load input is don't care. So now I have basically what I had before. So if I have Q or 0, the answer is Q. So now the Q output is basically what's going to show up to the D, and that's what I want to do when I'm shifting. So this is a very clever way of being able to have a parallel input, and also when I'm done loading the value that I want to load, I can do shift. So you would need this circuit basically at the input of all the flip-flops, and if I do that, then I can do parallel in. Right? So the advantages and disadvantages of parallel in is the advantage is it's faster because I only need 1 clock cycle. The disadvantage is I need more circuitry and I need more data lines. So parallel, serial, there's advantages and disadvantages to both. So it depends what you prioritize. But this basically is how you do it. So parallel in, once we have our parallel outs, parallel in, serial out, and parallel in, parallel out are basically both there at the same time. So if you want parallel in, serial out, you have the parallel input that we had before, and if it's serial out, you just look at that one output. If it's parallel out, you just look at all four outputs. So the output side of these is not much different. But that gives you all of the configurations of the basic shift register operation, which is serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. So that's basically the basics of shift register operation. The other thing we need to talk about is when you can shift bits, you can either shift left or you can shift right. So if you remember when you turn on the DE1 boards or the DE0 boards, you can see the lights going back and forth in the program that's built into that board. That's basically just a shift register shifting to the left and shifting to the right. Now, depending on where you read it, typically by convention, shift right is defined as moving towards the most significant bit. And shift left is shifting to the least significant bit. So shift left and shift right isn't always going to be to the right or to the left. It depends what your Q outputs are named. So if you're shifting from QA to QB to QC to QD, that's shifting towards the most significant bit, so we define that as a shift right. If you're going from QD to QC to QB to QA, you're going towards the least significant bit, so that would be a shift left. And that's true regardless of which direction it's going when you draw it on the board. So shift right is always towards QD, shift left is always towards QA. Now, if you want a bi-directional shift register, you're going to do basically the same thing that you saw for the shift load. It's almost the exact same circuit. So again, I'm just going to zoom in here and show you what you need to do there. Let me give myself a little more room. So let's say that this is QA, QB, and QC. So shift right would be going from QA to QB to QC. Now in this case it actually is going to the right, but it's shift right not because we're going to the right, but because we're going from QA to QB to QC. And shift left would be from QC to QB to QA. Now, in this diagram, we're only shifting in one direction. So if this is QA, QB, QC, QD, I would be shifting right. There's no way to shift left here because every time you clock it, the data is going from here to here to here to here. So if we want to shift left, we need to find a way to make it go from QD to QC to QB to QA. And the way we do that is with exactly the same circuit that we saw when we were doing parallel in, where you had to either shift or load, but not both at the same time. So this will be the same kind of thing. So if this is B and I'm shifting right, I have to go from QA to QB. But if I'm shifting left, I would have to come from QC to QB. So how do we do that? Well, we do it exactly the same way. The circuit will be exactly the same as what we saw earlier. So I have an OR gate going to the D input of the B flip-flop. I'm going to have my two AND gates. The output, again, of both of these will go to the OR gate. Now, if I want to shift right, then QA has to go to the D input of the B flip-flop. If I want to shift left, the C output would have to go to the D input of the B flip-flop. So C to B to A. So now all I have to do is do my decoder again. So again, I would just go, I would have an inverter here. This is the exact same circuit that we had before. So if I have, if I put a 0 here, then this will be a 1 and this will be a 0. So this gate will be disabled. This one will be enabled. And the QC output, so this will come out here, this will come out here, and the QC would go to the DB. So I'd be going from QC to QB. So that would be a shift left. So left, I'm going to put a bar over the left because if it's a 0, you're shifting left and right. So if I put a 1 here, then this is going to be a 0, this is going to be a 1, so this gate will be disabled, this gate will be enabled, and QA will come out here, and will come out here. This will be a 0, of course. So now QA will be going, I'll be going from QA to QB to QC, and that will be a shift right. So by using a similar circuit that we used for shift load, I can now, through this decoder, choose whether I want to shift left or right. If I put a 0 here, I'll be shifting left because the QC will come in to the B flip-flop, and the B will come back to the A, so I'll be going C, B, A, that's a shift left. If I put a 1 here, then I will be, then QA will make it to the B flip-flop, so I'll be going from A to B to C, and I'll be shifting right. Okay? So it's the same kind of circuit. So that's the basics of shift register circuits and bi-directional shift registers. So bi-directional just means it can shift left or right, and you basically just control it by whether you put a 0 or a 1 in this input. Again, the next time you turn on your DE0 or DE1 board, you'll see that the built-in program has a green and red light just going back and forth. So that's basically shifting left, shifting right, shifting left, shifting right, shifting left, shifting right, just over and over and over again. And this is what happens. Okay? So again, basics of shift register operation, the 4 different configurations. Again, this is serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. And for shift load and for bidirectional shift register, we just basically use this 1 to 2 decoder circuit, and then that allows us to choose whether we shift left or right. Now, the next topic I want to talk about is shift register counters. So these are a little different than the counters that we saw when we were just building counters. We'll be looking at 2 types of shift register counters. Again, you've probably seen examples of these many times before. Not the least of which is the robotic sign. When you're above the door, you see the LED going from R to O to B to O, T, I, C, S, and then it starts again. That's an example of a ring counter. That's what you're going to be doing in Lab 22. In Lab 22, you're going to build 2 shift register counters, a ring counter and a twisted ring counter, which is also called a Johnson counter. The ring counter you will be doing on the protoboard, or sorry, the ring counter you will be doing in Quartus, and the twisted ring counter you'll be doing on the protoboard. And the reason we picked that one for the protoboard is because it's easier to wire up. So the simplest one of these counters to build is the ring counter. And all you do for the ring counter is you're going to take your QD output and bring it back to the input. So basically, whatever data you have in that shift register is just going to rotate around there. Because what's on this D goes here, which means it 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 comes back to here. So this is the one you're going to build in Quartus. The ring counter is the one that's the circuit that you have above the door. The only issue with this one is if this counter starts at 0, 0, 0, 0, the ring counter will work, but it's just going to take all the zeros and just shift them around. So if you're just looking at the output, you're not going to see anything happening, even though something is happening. But the 0 that's on here will go here, the 0 that's on here will go here, the 0 that's on here will go here, the 0 that's on here will come back here. So all the zeros will be going around. So we need to find a way to get an initial value or an initial 1 in there. In this circuit, there's a couple of ways that you can do that. The first would be to introduce an OR gate. And then you could use this input to load a value in there. So if I make this a 1, this will obviously be a 1, and if I clock it, this 1 will appear here. And then you can just make this a 0, and then it's like the OR gate's not there, right? Because if you have, remember, if you have 0 or A, that just equals A. So if this input is 0, it's almost like this OR gate's not here, because this input will go straight to the output. That's obviously not what happens inside the gate. That's just for demonstration or explanation purposes. So if the input to this OR gate is 0, it's almost like the OR gate isn't there. But meanwhile, you've used the OR gate to put an initial 1 in here. And then you clock it just once so that you have a single 1. So these will all be still zeros. And now if you clock it, you'll see that 1 just bounce from output to output and go back to the beginning. This is exactly the circuit that's above the door. So if you clock it, this 1 will go here, this 0 will go here, this 0 will go here, and this 0 will come back here, right? So what the outputs will look like if you do this is the first output will be 1, 0, 0, 0. The next one will be 0, 1, 0, 0. The next one will be 0, 0, 1, 0. The next one will be 0, 0, 0, 1. And then from there, it goes back to here. So when you have a ring counter that's got a single 1 in it, and it's going around, the maximum modulus for this counter will be 4. And you'll notice that we have 4 flip-flops. So with a ring counter, the maximum modulus is equal to the number of flip-flops. So if you have 4 flip-flops in your ring counter, the maximum modulus is 4. Now, why do I say maximum modulus? It's because you can get a modulus of less than 4. So in the first example I gave you, when we didn't have an initial 1 in there and all the inputs were zeros, if I clock it, the next output will be 0, 0, 0, 0. The zeros all will moved around, but the output's still going to be 0, 0, 0, 0. And if I clock it again, it'll still be 0, 0, 0, 0. So that counter has 1 unique state, so the modulus would be 1. If I start off with 1, 0, 1, 0, if I start off with 1, 0, 1, 0, then I'd have 1, 0, 1, 0. The next state would be 0, 1, 0, 1, and then I'd be right back to here. So in that example, the modulus would be 2. If I have a single 1, then the maximum modulus, you'll get the maximum modulus, which is 4. So the thing you want to remember, and for the test, is that if you have a ring counter, so ring counter, the maximum modulus is equal to the number of flip-flops. So if I ask you to build a 3-bit ring counter, the maximum modulus will be 3. If I ask you to build a ring counter that has a maximum modulus of 5, then you just need 5 flip-flops. Now, the other thing that's peculiar to the ring counter is it is self-decoding. right? Because the number of flip-flops is the same as the maximum modulus. If you want to decode any particular value, and we've done a little bit of counter decoding in lab 19.3 and 19.4, if you want to decode any particular count, you just need to look at any one of the flip-flops, and that will tell you. So the two key things you want to remember about the ring counter is the maximum modulus is equal to the number of flip-flops, and that this counter is self-decoding. So of all the counters, the shift register counters or the JK flip-flop counters or the binary counters, the ring counter is the only one that is self-decoding. The slight disadvantage is you have to find a different way to get the 1 in there. Now we talked about one of the ways, which was introducing an OR gate to get that 1 in there. The other thing that you could do, obviously, is to use the clear and the preset inputs. So if I activate the preset input of this flip-flop and the clear input of the other 3 through a switch, then when and they're all connected together, when I make it low, this will put a 1 on QA and a 0 on all the other 3. So that's another way of introducing a single 1 into that counter, is to use the preset of one of the flip-flops and the clears of the other 3, and then when you activate that, you'll get 1, 0, 0, 0. And that's another way to get your 1 in there. Now, for the twisted ring counter, also known as the Johnson counter, there's a very slight modification, and basically everything is the same except you take the QD naught and you bring that around to the D. So it's very similar but has a profound difference. So the thing about the twisted ring counter, and the reason that we have that one on the proto board, is it's easier because this one is self-starting. Because if I'm taking the QD naught back to the input, if I start at 0, 0, 0, 0, if QD is 0, QD naught is a 1, so then that 1 will come back here. So I don't need a way to get a 1 into the counter, it will do it by itself. And there's a very unique pattern that you'll see on the lights. So if I start off with 0, 0, 0, 0, remember that the QD naught is a 1, so that means that 1 is going to be on this D input, so the next time that I clock it, QA will be 1. Now QD is still 0. Let me put these here above. QD is still 0, which means you're still going to have a 1 on this D input. So you're just going to move this 1 over. That will repeat again, and one more time. Now, once QD is 1, that means QD naught is going to be 0. So now you're going to start to put zeros on the D input. So now the zeros will start to work their way through. And then, since this is still a 1, you'll still have a 0 here, so then you'll be back to here. So when you run the counter from 0, 0, 0, 0 and let it go through here, you'll see that the 1s kind of appear in a wave, and then the 0s kind of appear in a wave. So if you run it like this, you'll notice that the modulus of this counter, or the maximum modulus, is 8. And we have 4 flip-flops. And what will always happen with this counter is the maximum modulus will be 2 times the number of flip-flops. So if you have a twisted ring or a Johnson counter with 4 flip-flops, the maximum modulus will be 8. If you have a twisted ring counter with 3 flip-flops or 3 bits, the maximum modulus will be 6. If you have 5 flip-flops, the maximum modulus will be 10. So the maximum modulus will always be 2 times the number of flip-flops. And the other thing that you need to know about this counter is It's not self-decoding, but it is self-starting. So in the lab, you'll be doing the ring counter in Quartus, and you'll be doing the twisted ring counter using the ICs on the proto board. So that's the theory behind these shift register counters. Now, in the lab, the chip that you're using will have many more pins than this. So it will have a QA, a QB, QC, and QD. It also has a QD not. It also has inputs to load. And it will also have a shift load pin. And it has a weird thing where it has a J and a K not. So we need to talk about that for a little bit. So we're basically operating with D flip-flops. This has a J and a K not, and we remember the J and the K from the JK flip-flop. So the reason there's a J and a K not is if you had a JK flip-flop, which hopefully you all remember fondly. Now, we remember that if J and K are both 0, that's no change. If J is 0 and K is 1, that's a reset, sorry. And reset, of course, means the Q is 0. If you have 1, 0, that's a set, which of course means the Q is 1. And if you have 1, 1, hopefully everybody remembers, this toggles. Now, if you had a JK flip-flop, if that's all you had in your toolbox, strangely, but you needed a D flip-flop, the best way to do that is this way. You would take a line to the J, and you would take an inverter, and you would send that to the K. If you do that, you've basically created a D flip-flop. Why? If the J and the K are inverted from each other, that means that they can never be the same. So they can never be both be 0, and they can never be both be 1. So that means this is gone, and this is gone. So if I put a 0 on D, I'm going to get 0, 1, which is a reset, so Q will be 0. And if I put a 1 here, then I have 1, 0, which is a set, and Q will be 1. So by taking a J, inverting what you send to the J and sending it to the K, by doing this, you've basically created a D flip-flop. So in the lab, you're just going to take your J and K and you're going to tie them together. And that's going to be your D input. Now, if you take this to the QD, right, you've basically done this, right? So you have your ring counter. That's what you're going to do in Quartus. Now, if you want to put, if you want to load a single 1 in there, you're just basically going to put a 1, 0, 0, 0. Then you're going to put a 0 on here to load it. You're going to clock it once, and then this 1, 0, 0, 0 will appear here. 1, 0, 0, 0. And then once you do that, you make this high again so that the chip will shift. And then you clock it, and then you'll have your ring counter. If you're doing the twisted ring counter, because you'll be doing the same chip in the lab, if you're doing the twisted ring counter, you will, of course, as we did here, you'll send the QD not back to the D, or in this case the JK not, which is really our D. And then you can just put the shift to VCC because you're not going to need to load anything because the twisted ring counter is self-starting. So when you're doing this on the proto board in the lab, you just need to tie the J and the K knot together. Just run a wire right to the QD knot and just make sure that the shift load is high. And then you can just ignore these load inputs because we're not going to use them. Okay. So when you do lab 22, I think it's 22.2 and 22.3 in the lab, if I'm not mistaken, that's how you will do this. So you will be using this chip. Just connect the J and the K knot together. You don't need an inverter because it's already inverted built in. So you just tie these two together. For the ring counter, you're going to bring them back to the QD. For the twisted ring counter, you're going to bring it back to the QD knot. When you do the ring counter, you will need to use the shift load and put a single 1 in here. You can put the 1 on A or B or C or D, it doesn't matter as long as there's just a single 1. And then when you do the twisted ring counter, you don't even need to use this, so just make sure it's permanently set up to shift. Okay? So that will cover everything that you need for the test, for this section of the theory. For the test, you'll need to be familiar with the ring counter and the twisted ring counter. You'll need to know what the maximum modulus is for each. And you'll obviously need to know how to hook them up and predict the output based on what the input is or the condition that I give you. So it's possible on a test that I could give you a particular output on the 4 outputs of a shift register, and I could ask you to predict what's going to happen if I shift left, or I could ask you to predict what's going to happen if you shift right. I think on the question I give you the choice of which way you want to go. Okay, so again, ring counter, the maximum modulus is the same as the number of flip-flops. For the twisted ring counter, the maximum modulus is 2 times the number of flip-flops. And the ring counter has the distinction of being self-decoding. The twisted ring counter has the distinction of being self-starting. And remember that the chip you are using in the lab will be this one. So again, JK tied together to QD or Q naught. So QD for ring counter, QD naught for twisted ring counter or Johnson counter. And that is the shift registers.